University in Atlanta. And part of that are many graduate students that you'll actually see some faces of in a little bit. So
Right.
what I want to be talking about is, what is machine learning? Why do you need high quality machine learning ready data set? We call ours a benchmark.
Dr. Martin, I don't think we can see your PPT if you are speaking from your presentation.
I'm speaking from my presentation. Yeah, you can't see it?
No, I can just see the screen on your desktop. I mean, have you shared the right tab?
It's can you see it now? Presentation overview?
No, we can't. I can just see the screen of your Google Meet.
You see this screen. Okay. All right. Let's try again. A window.
Typically, you have to say the full screen, then it works better than just a window. Don't share just a window. Share the full screen and then click OK or whatever in the bottom, and then that starts sharing. Share or OK in the bottom after you click on the full screen.
Okay, let's go there. Now I'm not allowed to share my screen. Oh, stop sharing here and then do it again. That's weird. No, I can't share my screen now.
I think you are logged in from two systems, so maybe that's why I'm hearing some echo. Meeting one is given all the access. Yeah, you are the meeting.
Can you see my PowerPoint?
No, not yet.
Can you see it now?
Can you just rejoin?
Say again?
Can you please rejoin? Maybe that.
Oh, rejoin. Yes, yeah. I'll do that. So I'll end this. You can hear me now, right?
Yeah.
Okay, now I'll share the whole screen, right?
Yeah.
Show you. Can you see it now?
Not yet.
How about doesn't want to, huh? Let's see here. Now I'm stuck again.
What is showing there? I mean, is there any permission issues related to that? Or?
Okay, let's try this. My entire screen.
You just need to click on that multiple window. So the which window or the entire screen? Now, yeah, now it's uploaded. Yeah. Now you can see your screen.
Okay, now I'll just bring PowerPoint to the foreground, and we should be ready. Can you see my PowerPoint now?
Not yet, actually. I think all you need to do is go to your PowerPoint and put it on full screen. It should work.
No, if he's sharing his full screen, then the PowerPoint should have come up. So I don't really understand this, why it's not working.
So have you opened your PowerPoint right now in your screen?
I can see it. It's on my screen.
I think then the problem is you have selected the window, and your window
No,
is selected for the this Google Meet.
I am sharing my entire screen.
Yeah, so that should so this is something else, some other problem going on. Maybe he can email the talk, and then one of you has to kind of go through it while he gives the talk.
I have
I said,
already emailed it. Somebody must have it.
well, I didn't see the attachment. Did you email it to me?
N-
Um,
to everybody, I think.
okay. Let's see.
Oh, no, just to the organizers.
Oh yeah, you have emailed the talk. No, you have emailed the abstract, but not the talk.
I did?
You emailed the abstract, but I didn't see the talk.
No, I know I
Uh,
emailed the abstract, but
not the talk though.
oh, shoot. Okay, let's try something else. Can I do it now? Yeah, that's even stranger. A window. You must grant permissions in order to screen share. Well, I just mailed a talk again. It's 29 megabytes. This shouldn't be too bad.
Okay, we'll just wait to see if you receive. Somebody can just put it up from our end. So how are things in Montana?
Great. It's beautiful at the moment.
You're spending the whole summer there?
Yeah, until, well, I start teaching August 15 again.
Okay, all right.
I got 6 weeks.
Hmm. We should catch up at some point in time.
Definitely. I'm on
Um,
WhatsApp now, so you can.
Yeah, I know about India trip, and there's something else is in the works, so I'll talk to you about it, perhaps
Okay,
in a
great.
separate.
Yeah, definitely. Okay. Did somebody receive my talk by email? One of the organizers. I sent it. I didn't get
No,
a
I have
note.
not received. So you have sent it to sesi@isarcol.ac.
Yes, I did.
Now I can see one new mail.
Okay, if you can bring
Yeah.
it up.
Yeah. Now I can get your PPT.
Okay, we're at slide 2 right now. And I'll just tell you next slide. Okay.
Yeah.
Are you seeing it now?
Yeah. Just 1 minute. I will see. Can you see it now?
Right, it's up, I think.
Can you guys see? Yeah, there it is.
Yes.
Good. All right. So let's go to the next slide. Hello? Yeah. Okay, so a brief overview. What is machine learning? Why do we need very high quality machine learning ready data sets, which we call benchmarks? What are best practices and mistakes to avoid when you start machine learning with data? Don't use black boxes. I'll get back to that. I'll talk about the projects at Georgia State and our databases that we have developed and are publicly available. And I'll talk about our work with NASA on the contract to develop predictive systems for the Artemis project, which is going back to the moon. And I'll briefly show that we have a lot of Indian students in our cluster, so I'll introduce them. Next slide, please. Hello? Okay. So machine learning is the study of algorithms that computer systems use in order to perform a specific task without explicit instruction. That's the key. So you don't tell them how to do it. You ask them to use an algorithm to find patterns in data. And those patterns, if you know them, you can use to predict events in the future. There is an automation of analytical model creation procedures. That's the new part of it. That's what it elevates it above statistics. And you learn from the data. This is not physics. This is pure computer science. That doesn't mean physics shouldn't be involved. So can I see the next slide, please? So I'll begin with a simple example that we did a couple of years ago in our group. That flare soft X-rays provide the crew on a spaceship alert for solar energetic protons. Solar energetic protons are protons that travel with roughly half or 1/3 of the speed of light. So they have high kinetic energy, and when they impact on human beings, they can cause cancer in the worst case, it can kill you. Now the soft X-rays go a little bit faster than the protons because they travel with the speed of light, of course. So if you have a big eruption on the sun and you're in Earth orbit, for example, you'll see the eruption after 8 minutes. Well, maybe your protons arrive after 24 minutes. So you have a little bit of warning if you see a sudden rise in X-ray flux. So if you look at the image left on the bottom, you see a quick increase to an X-ray flare. So that's a logarithmic scale there. Over time goes from left to right, of course. And then the proton flux increases almost linearly. And you can predict it. And the yellow thing on the right is what actually the system predicts that we built. And on the image on the right, you see what actually happened, and the prediction was, pretty good. So you can give a very short-term warning to astronauts to be safe for these high energy particles. And that means if they're in the spacecraft, they're usually safe at all, but they can hide behind shields, which they have. And if they are outside the vehicle, they can come inside in 15 minutes, maybe long enough. So this algorithm was produced by one of our students, Sukaina Filali Bubrahimi, when she was a grad student. She's now a professor. And the idea in the first nonlinear algorithm was, machine learning algorithm was produced by Marlon Núñez. But ours worked a little bit better because it was pure machine learning. So next slide, please. So how did we do this? This is a very simple, what we call classifier. Classifier is one back. Classifier is a method to make predictions. And it's very intuitive because it's based on asking questions of the data. is this flux, or is the derivative of the flux larger than a certain threshold, or is it smaller? And so the answer is yes or no, larger or smaller, and that brings you to the next step. So if you start from the top, you go to the next step, you ask another question, a physical question on the data, and then you ask a third question on the data, and then finally you come with a prediction. This is what's going to happen. So this is, you can actually see it. This is what a human might do as well, a good predictor. And in this case, we only needed 3 questions to get a slightly better result than an existing code on the first try. So the time lag correlation between the ghost proton channels, which measure the high energy protons, is an important decision criterion, unlike in UMACEP. So there's a physical interpretation in that. Now, the machine learning aspect of this is that those questions are not created by humans, they're created by the program. The decision tree program decides what the question should be so you get the best results. But you can see what the questions are, so you get some physical insight from the results. So next slide, please. So this is what a very simple drawing of what's going on. You have the Earth and the Moon, and astronauts in orbit, say, going to the Moon. The sun emits very high energy ions that you see there, which create a radiation hazard. The ions travel along the field lines, of course, and being able to predict them is what is necessary as soon as you go outside of the magnetosphere of the Earth. The magnetosphere protects astronauts, for example, those that are in the space station, because the magnetosphere deflects the high energy particles through the Lorentz force. So next one, please. Next slide. Okay, so why is this interesting? For NASA, at least. There are many reasons to why space weather is a threat, but in particular for astronauts, we have a program now to bring astronauts back to the Moon, and pretty soon, actually, within 2 years. And the next step in that program will be to create a space station, build a space station, not around the Earth, but around the Moon, which that space station will orbiting the Moon. And it will be subject to solar energetic particles, therefore, because the Moon doesn't have a magnetic field, no magnetosphere, so they're unprotected. And from that space station, astronauts will land on the Moon, and it will also, more in the future, be a stepping stone for expeditions to Mars. That's where they will start. So the astronauts are exposed, and they're specifically exposed when they're outside their space capsule. So when they're on the surface of the Moon, for example, walking around, and they need to be forewarned of any potentially lethal SCP events. So you need to be able to predict those events, and we're not really good at it right now. You want to predict them hours in advance, preferably a whole day, not just a couple of minutes in advance. So next slide, please. So our answer to that was to build a database. That's where we started with, to be able to predict flares more than, solar energetic particle events more than just a few minutes ahead. And to do that, you have to be able to predict flares and coronal mass ejection. So next slide, please. Okay, so what we made is the SWAN, the Space Weather Analytics for Solar Flares dataset. It's a dataset for benchmarking machine learning models for flare prediction. It's a multivariate time series, meaning that we determine data every 10 minutes or so from solar photospheric vector magnetograms on SDO. in space weather HMI active region patches, SHARPs, series that are available online. They're SDO HMI products. And it covers more than 4,000 MVTS data instances. I'll get back to that. And so far, we've cleaned up the data from launch of SDO in May 2010 until August last year, so 11 years. And it includes 51 parameters per active region patch, and it integrates over 10,000 flare reports. So clearly, if you see those numbers are so large, you need to have both a lot of people and a lot of software to be able to go and clean each of these data sets, because if the data aren't good, the predictions aren't good. That's pretty obvious. So next slide, please. Okay, so we did this and work, which was done by a lot of people, and you see there's a whole bunch of authors there in the paper. This paper was from Nature Scientific Data. It was an enormous struggle to get it published with referees who didn't like it at all, but that's the nature of the game. We did get it published, and with it, we made publicly available the data set for all those flares over 10 years now that we analyzed and cleaned up. So next slide, please. And to give you an idea of the group here, which is our astroinformatics cluster, on the bottom you see a group picture, which is a little bit dated because we haven't really seen each other in person for almost 2 years because of COVID. And then around it, all kinds of people that weren't even present at that group picture. So what you see is there's a lot of people involved here. And that's what you need to get the data right, basically. Not to do the machine learning. That's a simple part. So next one. So in creating data sets, there's a whole bunch of work that is involved. And the question was asked to computer scientists, what's the least enjoyable part? And if you see on the right hand on the top, cleaning and organizing data is the least enjoyable for 57% of those scientists. And all the other aspects of collecting data sets or building training sets, etc., refining algorithms, a much slower percentage does not like that. So the hard part is, and the hard work is cleaning and organizing the data. And that's why nobody likes it. And that's why we have such a large group, so we can chop it up in small pieces so everybody does their part and it's not overwhelming. Next slide, please. Okay. So here's an example of the data we derive from those active region vector magnetograms. And there's a whole bunch of them. They're like total flux, the average force-free alpha, free magnetic energy, and so on and so on. And from simple test, you can see on the right hand on the top that the red ones, which are intensities, which is, let's say, the mean force-free alpha, are the ones that are, sorry, the totals are the ones that are the most predictive. So the best predictor for a active region flaring is the total amount of flux, which is no surprise, of course. The more flux, the more magnetic field, and the more likely an event will happen. So the benchmark data sets are data set used for benchmarking a particular class of algorithms and systems in computer science. And why do we have those? If you want to compare different methods of machine learning to see how successful they are for specific problems, say flare prediction, you have to test them on the same data set. Otherwise, it's meaningless. A person can write a paper and say, okay, I calculated my flare data, ran a machine learning code on it, and these are my skill parameters. This is how well it does. And then somebody else runs a different method on a different amount of set of data and gets another result, but the comparison of the skills of these two is meaningless. So what you want to have is a benchmark that's a data set that's really very thoroughly cleaned and that everybody then can play on with their best machine learning algorithm for that specific problem. And in computer science, they're called benchmarks, and our solar physics referees didn't like that term at all, but we showed them that it's really valid, and then it happens. So it's used for standardized testing, for validation, for comparing different methods. It's ease of access. It's there for everybody, for the whole community, and it's usable. It's presented in a form that you can insert it directly into machine learning algorithms. So, for example, an Excel spreadsheet is usually good enough, but you can also use some kind of data storage mechanism. All right, next slide, please. So the term benchmark has different meanings, and the meaning we use is the third one: a standardized problem or test that serves as a basis for evaluation or comparison. Sorry, as in computer system performance. So next one, please. So data quality is really the essence of making good predictions. No surprise, it's the same thing with when you do numerical simulations. So the driver for data quality problems is usually a lack of strategy. People just throw a whole bunch of data sets together, which have different resolutions, different intervals, and sometimes even different data, and hope to be able to predict from that. And that's not, the computers, the algorithms aren't smart enough to do that. Usually humans aren't either. So what you want is a completeness. You don't want gaps in the data, unexplainable gaps. Say all of a sudden you don't have any active region data. That means that the algorithm will think there are no active regions on the sun, and if there are flares, which are measured by other instruments during that gap, then it's hard to explain how these flares could come about without there being a magnetic field. So you have to have consistency. Already touched upon that. You want similar resolution, similar data types. You want accuracy. Are your data correct? Very important. You want validity. Can we validate the correctness of the data as a way of testing it? And timeliness. Are we getting the critical data in time? And this is for when you want to have a predictive system, say for astronauts on the moon. You have to have your data in and cleaned to make a prediction in time for the next day. So why does it matter? Well, the results and the models are affected. When you don't do those things, you get bad predictions because you don't put in bad data. Garbage in, garbage out. All right, can we have the next slide, please? So here to show you again, these are all those parameters we measure. So flux, free energy, mean alpha, potential energy, etc. And for every time instance, every 10 minutes, all those parameters are calculated, which is a lot of work. We had to write our own codes for it because the codes online weren't that good. So you have a data there. There's a time instance. There's a location on the sun of the active region. And you have 50 data points for all these different parameters that we calculate from the vector magnetogram. And the question is, can these parameters be linked to the occurrence of a flare and the strength of a flare? So from a different instrument, from ghost data, we find the strength and the location and the time of a flare. So an X9 flare, say, for example, at active region 2078, and so on. And then, so the input is these data from the active region, these magnetic data, and what you're trying to predict is the flare, its location, its timing, and its strength. And you can look at that as a simple computer science problem. You've done the physical science now you're just looking at a set of numbers on the left-hand side and another set of numbers on the right-hand side, and can you use those numbers on the left-hand side to predict the numbers on the right-hand side? That's one way of looking at it. And computer scientists will do that very often because they know almost nothing from solar physics. It's one of the reasons we work together as a group, because sometimes the physical information is just as important. So go to the next slide, please. So there are two common misconceptions in doing machine learning. The first one is that algorithmic development is the only driving factor behind the data-driven discoveries. That is, if I make an algorithm that is good enough, I'll find the results, no matter what. That's not true. Bad data will give you bad results. And so you get those, you often see those problems that people will find a new method and algorithms, say deep neural networks. They don't understand what they are or how they work, and they apply them to really bad data, and the result is pretty bad. And the second one is more data is better. That's not true. If you add data that are not as good quality as the data you already have, you're actually not improving your predictive capabilities. So the quality of the data is really the key point here. And if you add spurious data, your predictive capability will go down. So next slide, please. So what we've been doing is, this is what's really the hard work, get all these data together. So we have the HARPS from SDO HMI, we have the NOAA GOES flare reports, we also have SSW latest events reports, just to double check. We look at flare reports from Hinode, and we have the NOAA GOES X-ray flare data, of course, and then the NOAA active region report. So there's several data bases to start with, and then you have to compare that they actually refer to the same events. For example, NOAA active regions, which their locations are given by human beings, they put them in. They sometimes make mistakes. Instead of 70 degrees or 37 degrees north, they'll put in 37 degrees south. And if there's a flare, it's 37 degrees north, then you have a mismatch there. So you have to check that. And we did that. We basically built routines to do the checking, so that those routines will alert you if something funny is going on, and then a human will look at it, one of our large team. So in the end, what you come up with is a very clean data set. Next one, please. So flare forecasting. Now we have our data set. We even got it published. We put it online. Everybody can use it. And now we started, of course, doing some flare forecasting to begin with. So that's what I'm going to talk about next. Next slide, please. Okay, so we use classifiers. Classifiers are algorithms that you can use for machine learning for predictive capability. So a classifier is a machine learning forecasting algorithm. Now, how do you train it? You train a classifier on 2/3 of the data for a given period. That is, we input the data, both the predictive, the magnetic field data and the actual events. And that classifier will then figure out for itself what the relation is between the magnetic field data and the actual flares. So classifiers are typically off-the-shelf software that you can just buy or get in Python, for example. You don't really have to do a lot of work on those. Computer scientists spend a lot of time building better classifiers or improving existing classifiers, but for most of the users that really don't do that. Then you test your classifier, the remaining 1/3 of the data, and you make the classifier do predictions, and you compare that to the actual data set. How well did it do? And there are ways to make that quantitative, and I'll show you that. But that's not the end. Say you've used your classifier, the 2/3 of the data and the test, for 2 years worth of flare data, say 2015, 2016. Now you're going to verify performance on a different data set, say the flares from 2017, and see how well it performs on that. And from that, you determine skill scores, which is just a mathematical quantity that is supposed to describe the skill. Now, different classifiers you want to compare. You want to know what's the best classifier for this problem, and computer scientists want to build classifiers that work even better than the older ones. So in order to compare them fairly, you need to work with the same data set, and preferably a very clean data set. So if you look in the computer science literature, you see that there's only like 9 or 10 data sets that are used all the time to test classifiers out. Next slide, please. So examples of classifiers are naive Bayes, support vector machines, k-nearest neighbor, decision trees. I already give you example of decision trees, as etc. And often they're used as black boxes, which is a bad idea. So if you click on that, you get another line, I think. Common sense in machine learning. Yep. So when you encounter a black box, my suggestion is look inside it. Try to understand how it works. And even with fairly complicated classifiers, such as deep neural networks, it really helps you a lot to read 2 or 3 papers that describe how they work, what their function is, and how they can be modified. That way, you avoid pretty obvious beginner's mistake in using it as a black box when you use it in a way that's not supposed to be used. So next slide, please. And that, oh, sorry, I forgot. That's why we work interdisciplinary at Georgia State, because our computer scientists that we work with, they actually understand those classifiers better than a typical solar physicist. You can only have a PhD in one field. So we need balanced data sets. And here is what a very funny example where all that the classifier does is going to predict whether there's a flare. Nothing said about the strength, or there's no flare. And what you see there is what we call in solar physics a truth table, but computer scientists call it the confusion matrix. So you can have really big misunderstandings between people from 2 different disciplines because you're not speaking the same language, really. So one of the things we did is actually make a dictionary from computer science to solar physics and vice versa, so that we can talk about the same things. Labels don't mean the same thing in computer science. Events don't mean the same thing. Features don't mean the same thing, and so on. So let's look at this confusion matrix. So we predict the flare, that's the first column, and there actually is a flare, 58 cases. Then there is a flare observed, but there's no flare predicted, 13 cases. So here we clearly missed the boat with our algorithm. Or we predicted a flare, and there's no flare observed, which is a false positive, 23 of those. And then you see no flare predicted, no flare observed, 10,230, clearly the overwhelming majority of all cases. And that's what we call an unbalanced data set. So the events, in this case flares, are very rare. And the same is true if you, for example, try to predict earthquakes or hurricanes or tornadoes. Those are all relatively rare events, and they're really hard to train classifiers on properly. Because what happens with the classifier, looking at this result, classifier will say, hey, well, almost all the time there is no flare, so I'm just going to predict there's never is a flare, and I get it right 99.9% of the time. Really high skill scores and totally useless for us. So an unbalanced data set leads to high skill scores and no predictive capability, which is garbage. So we have to deal with that one way or another. So next slide, please. And here we do a couple of experiments we did with our SWAN data set. So first we just run support vector machines on unbalanced data, which I just told you will give you terrible results. Then experiment A, we do support vector machines on undersampled data. So we just threw away 90% of the cases where there was no flare. Experiment B is oversampled data. You can just multiply your cases of flares with flares that are just like it, with the distribution that is similar to the really observed flare, and that's called oversampling. That sounds a little bit fishy, but it's actually a useful method, as has been shown for other problems. And then there's experiment C, where the penalty for doing one prediction wrong and one prediction and the reward for doing a prediction right in your classifier are different. So you get a big penalty for predicting a flare and there is no flare. You also get a big penalty for missing a flare, but you don't get much penalties for missing quiet regions. And then the experiment X was where we use a different classifier, namely a decision tree, a very simple one, and see what the results are. Okay, so what are we trying to predict? X and M flares, and C, B, and nothing flares are, in our case, no flares. We don't use climatology for now. That means we don't look at variations over the solar cycle, which certainly exist. It comes later, and we look at simple, only one value of our time series, which is a bad approach, but just to let you see it for now. So next one, please. There's a performance measure, and there are many performance measures, but true skill statistics is perhaps a better one. It varies, TSS varies from -1 to +1. It's a really bad when it's around 0. It's excellent when it's close to 1, but it's also excellent when it's close to -1, which means that you consistently make the wrong prediction, but that's no problem. If you consistently predict a flare when there's no flare, and you consistently predict no flare when there's a flare, your score is -1, but it's still a very good result. You just need halfway intelligent people to turn that around, right? When you have a TSS of 0, you're not predicting anything right, really. It's just random. So let's move on to the next slide, please. So again, class imbalances. This is what comes from our data set. We made 5 partitions, which are partitions in time, with each relative having about relatively the same amount of flares. So you see partition number 3 in the middle there is doing solar maximum. We have the most flares. And you have these imbalance ratios of 58:1, 69:1, etc. So that's, and worst case is 95:1 at the end of the current solar cycle. So that's really bad. So we have to do something about it. So next slide, please. Okay, so here we do no class imbalance remedy and get a couple of results. So the TSS scores for different time intervals are shown here by those bars, and they're really low. They say 1/4, 0.22, some are 0.04, which means absolutely no predicted value. It's not good. So let's try to do something about the class imbalance. Next one. Next slide, please. Okay, so the little blue bars are again the ones with no correction for class imbalance, and with undersampling you get sort of the dark purple bar. With oversampling you get the light purple bar, and with weights for different penalties for different mistakes, you get the almost red bar, and that's actually the best result. So then we get true skill scores in the order of between 0.7 and 0.8. That's pretty useful. And with weights, we get a little bit higher. We get typically of the order of 0.85, which is close to 1. I don't think that's good enough for helping astronauts yet, but you can still miss really big flares. But maybe this is as good as you can get with the data we're using. that we don't know, and that's what we're looking at now. But anyway, these are pretty good results that definitely NASA is very happy with. So let's look at the next slide. And now we've actually made time series of the data, as I told you early. And this was based on single points. Now we look at times the whole series. What if you use the whole series prior to a flare as a predictor rather than just one point in time? And then you get better results. The purple ones, again, are better than the last value TSSs. So you get a small improvement, which is definitely significant, but definitely not as big as we had hoped and as I had expected from just intuitive physical reasoning. Nevertheless, it's better to use the time series than the single points in time to do your prediction. And you get, again, values typically around 0.8. So next one, please. Okay, so let's try something else. Let's try decision tree, which is a different classifier, a different algorithm. And again, we use no correction for class imbalance, undersampling, oversampling, and weights. And the results are pretty much the same as we'd had with support vector machines. So clearly, between those two classifiers, you cannot really say who's the best. We use other ones. I don't have slides for that here because of work that's been done later and has been published now. If you use neural networks or deep neural networks, you still get similar results. So it's not very dependent on the classifier, which is actually a very encouraging result. So let's do the next one. So it's still talking about prediction of flares, right? But what we really want to know are solar particle events, because that's what kills the astronauts in the worst case. And it actually can do a lot of damage to spacecraft as well. So let's go on to solar particle event forecasting. Now, they come in two flavors, solar energetic particles again. The narrow cone event, which you see on the left, where you get a very sharp increase in particle flux at the GOES satellite, which orbits the Earth, and then it goes down slowly. And then the one in the middle shows you a very gradual increase in particle energy flux, so much easier to predict. Go back. And then on the right, nothing happens. There's a big flare, but the magnetic field coming out from the sun doesn't go to the Earth. So the high energy particles don't really touch us. That's what happens on the right-hand side. So the hard part to predict is the really rapid rise in particle fluxes. And that's probably because those particles are accelerated close to the sun in the flare itself, in the two-ribbon flare. Well, in the middle case, they're probably accelerated by the shock in front of the coronal mass injection. But that's an interpretation. There's still discussion on that. So let's go to the next one. So this is what we want to predict, knowing there's going to be a flare or that we're predicting a flare. Now, again, those SCPs are very rare. The class imbalance is extreme because not every flare leads to an SCP. So there are more flares than SCPs. The number of SCP events in cycle 24, which just ended, is extremely low because it was a very mild cycle. You're dealing with heterogeneous data sources because we have CME speeds and so involved, which you have to derive from LASCO data. That's not a trivial matter. Spatial and temporal resolution varies a lot between, say, LASCO, AIA, and GOES, of course. And then there are frequent data gaps, especially with GOES. Not all data is available for all the events, so you really have to clean up very carefully again. So can I see the next slide, please? Now that database we just completed. And that was done actually by a graduate student of mine, Sumant Rathi, who's Indian, by the way, as part of his thesis. And he has a thoroughly vetted machine learning ready database that contains about 350 Earth impacting SEP events, so solar energetic particle events, storms. That paper is going to be published in AppJ supplement, and the database is already available online, as is the paper on archive. Sorry, and Sumant is now working on machine learning tests of this database. But as you can see, this is a very hard problem. We only have 340 impacting events starting from the mid-80s. That's when you had the first data. So very few. And this is not going to be simple at all. Nevertheless, this is what needs to be predicted for the astronauts that go to the moon. So next slide, please. So we have this contract with NASA, the Space Radiation Analysis Group, who is responsible, that group, for giving predictions and warnings to the astronauts in deep space. Of course, NASA is not completely stupid. We're not the only group that's working to make such a system. They fund 3 or 4 different groups at different places, and they do one themselves. I think we're the only university, though. And they'll just use the input from the 4 different systems that are being developed. They're not going to pick out the best. They're just going to combine the input from all those systems and hopefully get the best prediction for that. So our system will look, when it's completed, which is in a year or so, and we'll look at active regions, location, properties. It makes a flare prediction from that. So it looks at the magnetic field in active regions. You need a vector magnetogram. We get a predicted flare class probability. So if we know there's going to be a flare, then we can predict whether there's going to be a CME with that flare. And that's the link we're working on now, to find the right qualities in a flare. Can you go back, please? To predict the CME. And once you have a CME, there's a good chance that there's an SEP, depending on which direction the CME goes. And so there we try to predict the possibility of SEPs. And what NASA in particular is interested is not so much the warning for an SEP, but the prediction of a quiet phase. So for the next 24 hours, there's not going to be a solar energetic particle event. And then they can do whatever they want to do on the moon. So all quiet is really the most important prediction. And of course, intuitively, you can see if you look at the sun and you see no active regions around solar minimum, that's probably when you have an all quiet result, or you have just very weak active regions all on the east side, near the east limb of the sun. Probably nothing's going to happen. But we want to get this as precisely as possible. So this is the system we'll come up with in the end. We'll deliver that to the CCMC, which is the community coordinated modeling. Sorry, I don't know what CCMC means anymore. It's an organization at NASA that tests and collects prediction.
Community Coordinated Modeling Center.
There you go. Thank you.
Welcome.
So they actually have scoreboards for people who have delivered predictive models already, either through simulations, numerical simulations, or to machine learning. And they see in real time how well they score, so they can make comparisons, which is a very useful thing. And we'll deliver our systems to them as well. We're already talking to them. So next slide, please. So our timeline is we're roughly at 2022, or we're exactly at 2022. So we're at phase 4 of our contract, and we're making rapid progress because Sumant and I started working backwards from the SEPs themselves. We already have the catalog, as you can see, and we're working on prediction methods. So actually somewhere before 2024, we'll be ready with that. And then our goal is an embedded and real-time system for SCP prediction on Artemis 3 spacecraft. So that's the third launch of Artemis, where there will be people on board going to the moon, which probably happens in 2024. The first launch of Artemis will actually be in September. It will be an unmanned spacecraft, but still going to the moon. Actually, I really want to go to Kennedy Space Center to see that. So this is going to be quite an event. So we'll see the next one. Next slide, please. Almost done. This is actually my my final slide. End goal, back to the moon. This is really amazing that more than 50 years after humans first landed on the moon, we haven't been there for almost 50 years. And we basically end up building a rocket that's very similar to the rocket that went to the moon, Saturn V, which you see on the left. The only thing that changed is that the rocket is now on the other side of the launch tower, if you look carefully. And the other thing that has changed, that part of this rocket is reusable. We'll come back to Earth, and that will reduce the cost of launching by a large amount. So far, we already NASA has already signed agreements with ESA, with Japan and Canada on the Gateway space station orbiting the moon. I definitely hope that India will join as well, because India has a lot to offer. And I'd like to get the next slide now, the final slide. If you can. Is there a next slide? Should be. Yeah, there. Okay, so I want to emphasize my India connections here. We actually have a lot of students from India in our group. I'm not listing all of them, only the ones I work with. We also have a lot of students from Islamic countries. We all seem to get along just fine. So in the middle there, you see my good friend Dibyendu, who I've been working with for 20 years or so. Always been fun. And on the left, you see Aparna with a very long last name. She's from South India. Venkataramana, I think. She's a NASA Finest Fellow and a DKIST ambassador. She works on solar eruptions, in particular filaments. With me, she'll graduate in a couple of months, and then we'll have a job in the Bay Area. Sumant Rathi on the left bottom, sorry, I already mentioned, he's also a NASA Finest Fellow. That means he won a grant to pay for his graduate education. And he works on solar energetic particle storms, obviously. On the top right-hand side, you have Sushant Mahajan, who was a GSU second century fellow. He got his PhD a couple of years ago. He has collaborated on that big paper that I showed you of the SWAN SF database, and done excellent work on meridional circulation, and done some more work that he still hasn't published yet with Dibyendu and me. So I'd really like him to publish. And he is at the moment a postdoc at Stanford. And then we have Sumitra Hazra, who was a postdoc in our group. And he worked with me, at least, on filament chirality analysis comparison, and a really nice paper, also producing a database and comparing with machine learning results. But he has also done work on dynamos with Dibyendu, and now he works on solar wind modeling. So that's it. That's my talk. I'll be happy to answer any questions you have. And thank you for your attention.
Thank you so much, Dr. Martin, for that great talk. From the participants, does anybody have any question? You can raise your hand or unmute your mic to ask. Yeah.
Yeah.
I think you can unmute
Hi.
and go ahead.
Hi, Pete. So this is Soumya from SESI.
Yes.
So I wanted to ask you about the prediction window, the SCP events that you are trying to forecast and issue alerts. So what is the prediction window? I mean, what is the time before which we will be able to, up to a certain precision, will be able to determine that this is going to be a severe, there is going to be a severe solar particle event, so that we can
Yes.
stay prepared?
We tried two windows. One is 24 hours and the other one is 48 hours. Obviously, for the 24-hour window, you get better results than for the 48-hour window. And we look back in time about 48 hours to the data of that same active region to see how it develops. So basically, the planning for spacecraft operations has a 24 or 48-hour cycle. So that's what this is determined by. And what it assumes is that we can very rapidly retrieve the data from GOES and from SDO and convert them into useful input for our mechanism. But NASA will, of course, take care of that because they have a big interest in making that happen. Does that answer your question?
Yes, yes, yes. Thank you.
So I'm predicting, or we are predicting flares, right? And flares lead to SCPs. So we're going to say, okay, there's so much chance of a flare, there's so much chance of CME, and because of its location of the sun, there's so much chance of a SCP, and that's really the end of the thing. So you can predict the flare correctly and still get the SCP wrong. It's a very it's a three-step bootstrap prediction.
Correct. Yeah. Thank you.
Mhm.
Can I go ahead and ask a question, Yoshita?
Yes, of course.
Pete, hey, that was a fantastic talk. Thank you very much for signing in this late from Montana. My hellos to Kathy and the kids, they're still around.
Well,
So I had a question for you. You talk mostly about parametric inputs into your machine learning algorithms. Did you
correct.
try using images, or do you? I mean, you must have tried this. Do you really find any significant improvements, or you find that the parametric inputs are good enough? And of course, they're much more efficient, so that
Yeah.
way, for it more efficient in terms of computational timing.
There are people who have looked at, say, simply looked at AIA data and just input them in a machine learning algorithm without any interpretation and tried to predict flares from that. I don't think that it worked as well as our methods have, but it's certainly an approach that can be taken, but we've just chosen not to take it.
Okay.
One of the things of using these parametric inputs is that you actually learn what is really important in predicting a flare, which of these 50 parameters really are decisive. And clearly, total flux is very important, but you know, with a little bit of physical intuition, you can understand that. Another parameter that we found that I really find interesting that is important is the current helicity. So that's the integral of J dot B, as you know, which tells you something about how strong the currents are with respect to the magnetic field, if I understand it correctly.
Right. Yeah, I think I agree with you in the sense that there's certainly more physics that you can clean out of this parametric approach.
Okay.
So I don't know whether we'll have time, but if you can, try to stick around for Shubhadeep's talk, which is the next talk. So he is just graduating from SESI. He's my PhD student. So we just completed our first work on applying machine learning to solar flare forecasting with some computer scientists and well, solar physicists.
Mhm.
And we have some interesting stuff to show. And he's also in the market. He's looking for.
Okay. Yeah,
All
he's
right.
about-
Great seeing you, Pete. I hope we can see you physically sometime in India soon.
Yeah, I'd love to be back. I haven't traveled in years because of the stupid COVID.
Glad to have you back. All right, I'll give it up for others.
All right.
I have a quick question. Has there any, any attempt being made at predicting CMEs that are not associated with flares? And if so, what are the kind of inputs that you would like to feed into the model?
Right, right. I think as far as I know, almost every CME has a flare, but not necessarily a strong flare. It could be a C-class flare or even B. But the input for the CME prediction is the same as the input for the flare prediction. It's the magnetic parameters of the active region.
Okay, thank you so much. Are there any more questions from the audience?
I have one quick question. So this is Subodhi from CC. Thanks for this nice talk. So first of all, and so I find that you have shown some histogram distributions for tackling the class imbalance problem. So, and in that slide, you have mentioned that we can get the best score with modifying the weights. So why this is better performing better than the other undersampling oversampling? Can you just give us some comment?
I really couldn't tell you. That's not that's not a paper that I've done. It just works better. That's all I can say. But yeah, it would be a good idea to try to understand that in physical terms.
Okay, thank you.
If there are no more questions from the audience right now, we can move on to the next talk. Professor Martins, you can probably hang around, and if somebody has a question in the chat, you could probably take that in the chat box. Yeah, thank you so much. That was a great talk.
Thank you.
Next, we have Shubhadeep Sinha from SESI, and he'll be talking on identifying flare productive active regions using a machine learning technique.
Okay, just 1 minute. I will be signing out from this account and let me rejoin just. So I'm sharing my screen. My screen is visible.
Yes, it's visible.
Is it full screen now?
Yes, yes, it's on full screen.
Okay. Okay. Should I go ahead?
Yeah, of course.
Yeah. So, okay. Hi, I'm Subhadeep from CC, Aizer, Kolkata. I will be talking about the identifying player productive active regions using machine learning techniques. So, as we know, basically, Sun is a dynamic star and it has a magnetic field. And this, due to the solar rotation and referential motion, the magnetic field basically changes over time. And due to that, there is often some regions with high intense magnetic field occurs on the observed on the sun solar surface, which is called the sunspot, and the active regions you can see in this the middle one image. So these are intense magnetic field regions, and so the magnetic fields near these regions are many times are such organized in such a manner that in two oppositely directed magnetic field comes closer, which gives rise to a situation where magnetic reconnection can take place easily, and by this process intense amount of energy is radiated in terms of electromagnetic radiation, which is known as the solar flares. So in the left panel, you can see this is a example image of the solar flare. So this is captured by uh, atmospheric image assembly in the 131 angstrom channel by HDO. So it's a high X-class solar flare events, and you can see in the middle panel, which is basically gives the magnetogram image captured by HMI magnetogram. So the the second panel is magnetogram image basically captures the magnetic field maps on the solar surface. So the white regions, white color basically specifies the magnetic field which is going out, and the black regions are giving the magnetic fields which are coming into the solar surface. So you can see there is a sunspot beneath the clearing regions, and also as these are very energetic events, so most of the time this energy, a part of this energy is you manifested into the local plasma materials on the corona, and which are ejected out due to these eruptions, which basically gives us a phenomena called the coronal mass ejections, which is shown in the right side panel. So you can see as this is the center is the same events on AIA 304 angstrom channel. So you can see that there is a flare brightening, and which basically um, ejected some amount of plasma material into the interplanetary space, which we see in the coronagraph image. So the outer portion is the Glasgow coronagraph C2 field of view, where you can see these particles are ejecting out. So why this is important to identify the flares and the corresponding active regions. So because so as I have told you that these energetic events can cause the coronal mass ejections, which, if that is directed towards the Earth, it can cause various space weather effects and impacts the human life. So as in the previous talks also, we can see in the Benus talk itself the space weather impact on for these eruptive events. So I will not talk about more detail onto that. But so the major sectors which are highly susceptible to this kind of eruptions, that are basically uh, the navigation and the satellite which are revolving around the Earth, because these are the more outer layer of the human technology which is on the space, so they are highly affected due to these events. And it also cause the impact has an impact to polar route airlines, because the impact is higher on the Earth's pole, because there is the magnetic field lines are open and the particles are trapped in that region. So also it has astronomers health there is a concern on astronomers health for this for identifying and predicting these events, so because they can expose to high amount of radiations. And another one is the phenomena which is aurora, which is you can see in the northern and southern hemisphere, you can see this kind of lights. Mm, so this is a beautiful phenomenon. Only this is, I mean, this doesn't has any effect on humans' life, and this is only a good thing about this energetic events. Um, so so for any machine learning model, so the major steps, the first major step is the data preparation process. So in this work, we have prepared collected the data from Hinode and Ghost player catalogs. So for we have collected the data during the May 2010 to December 2020, which is approximately 10 hours, 10 years of data, covering the almost the once of entire solar cycle. So and so first of all, we identify the similar events for these two catalogs, so that we can match the events, which gives us, I mean, if any events has a entry in both the catalog, we include these events in our analysis. So we basically look for a 2 minutes window. So if for any events which is listed in goes as Hinode XRT catalog, if the same intense if the same flare events is also listed in the Ghost catalog with the same intensity, um, and the timing flare peak time falls around within plus minus 2 minutes, we call them identify these two as a same events, and we take all those events. And so by this process, we have total in our dataset, we have identified total 503 M and X class flares, and 3,358 below C class events. So we are our flaring dataset, which we call as a positive one, that consists of this 503 M and X class flares, and our negative dataset, which has a this 3,358 events, which has intensity less than C class. Okay. So we use HMI sharp vector magnetogram patches for this preparing the data. So we first of all calculate various features from this vector magnetogram, which magnetic features, which basically uh, characterize the active regions behavior and the non-potentiality of the active regions. So so for all these so here is an example in the right hand side of the Z component of magnetic field for sharp patch. Similarly, we have the X and Y component. So from these three components, we can calculate various magnetic parameters like unsigned flux, total current, helicity, and these things. So so all these features we have calculated for a flaring event. We calculate all these features 24 hours prior to the peak flare time, and this represents these features represent the event in our feature space. So the the idea is, if any after the uh, after training the model, so if our model output is saying this, if a region is falls in the identified as a flare positive events, so then this should be and this should cause a flare in next 24 hours. There is a high chance. So this is the idea. And so in this table, so I have shown that the number of input features that we have used for this characterizing these active regions. So we have started with these 19 magnetic features. So these are R values, and which is basically the sum magnetic unsigned flux over the integrated over the magnetic polarity inversion line, and then the unsigned current, the total absolute twist, the current helicity, and mean potential, like this. So some of these features are directly available in the sharp header file of this sharp data. So we don't have to calculate explicitly those things. We can directly import those data from the header file, and there are some other uh, features which we need to calculate, which are not available in the directly available. So these are marked with the asterisks. So like so these 6 features we have calculated. Yeah. So these are shown in the with the asterisks. Yeah. So now to to get the what are the out of these 19 features, there may not be all features may not be the equally good. So just to filter out, I mean, just to um, uh, identify which features should we use, and which has a more importance for this classification, we first use a ANOVA statistics score. This test basically tells us the between class variability by intra-class variability. So basically, if the positive uh, positive events um, are clustered, separated, the positive events and the negative events are separated largely, then we have a higher ANOVA test score. And if they are mixed up, we have a comparatively less F score value. So these F score values are shown in the right. So you can see in their higher maintaining the order. So that from the top we have a these are normalized values. So we have a span of from 0 to 1. I mean. So you can see the last 5 features, which has a very small F score values. So we discard these 5 features, and we focus on the top 14 features, which is shown in the red bounding box, and we proceed with these 14 features for the further study. So now to estimate a model performance, how the algorithm is working, machine learning algorithm, we need to quantify the model performance. As in the previous talks by Dr. Martins also has shown the how these performance indicators can be calculated from the confusion matrix or the truth table, whatever you can call. So these are basically 2 by 2 matrix, which has with the 4 elements, with the true positive, true negative, and false positive, false negative. So true positive basically gives us the number of positive. I mean, in my case, in our case, so positive means basically the flaring events, and the negative means the non-flaring events. So true positive basically gives us the number of positive events which we have the model has predicted correctly. Similarly, the true negative is the number of negative events which our model predicted correctly. False positive is the falsely identified positive events by the model, and the false negative is the falsely identified negative events. So with these 4 values, we can construct various performance indicators. So true skills statistics or true skills score is one of them, which is majorly used in this community. And so this can be represented with this formula: true TP by TP plus Fn minus false positive by Tn plus Fp. So the benefit of true skills score or true skills statistic is that so it doesn't depend on much on the class imbalance ratio of the data set. So as in these kind of scenarios, we have a very less amount of flaring events compared to the non-flaring events. So our data is always uh, uh, suffered with this class imbalance problem, and so in for these reasons, the normal accuracy or recall that doesn't give us a as a good estimator for judging the models. But true skill score is very useful for that. And we can also use the macro accuracy, which gives us the average accuracy for both the positive class and the negative class. So apart from this, we have also introduced two new space weather metric that are called severe space weather and um, yeah. So we have introduced two metric, which are severe space weather or SSW, or the clear space weather or the CSW. So the motivation behind introducing these two metric is that SSW basically deals with the positive events. If you can see in the other metric is TSS or macro accuracy, all the four elements of the confusion matrix are involved in estimating this metric. But if we want to look at our model, how the model is treating individually for the flaring events and the negative non-flaring events, for that purpose, this SSW and CSW is very beneficial, because you can see for the calculation of SSW, this gives only the number of correct identification of the flaring events minus the falsely identified flaring events. I mean, falsely identified in that group, because the denominator is basically TP plus Fn, which basically gives the total number of positive or flaring events in that class. And similarly, CSW gives the denominator basically tells the total number of non-flaring event in that class. So, so this basically helps us to uh, judge how our model works for a particular class, if it has any bias towards that class or not. So now I'll talk about the method of analysis for our training, and so we first randomly shuffle our dataset uh, into 20 we make 20 replica of the dataset by random shuffling process. So just to make it more robust statistically, and we perform our analysis on each of these 20 dataset, and finally our average result will give the indicates the performance of each model. Okay. So we divide the dataset 80% to the training to train the model and 20% for testing purpose. Now each of these models has various parameters, optimization parameters, which need to be tuned to get a proper, better results for a specific problem. So these model parameters we have um, iteratively changed over a various over a range, and with these various values of the optimization parameters, we check the model performance on the validation data set. We also use tenfold cross validation to make it more generalized. So from this uh, from this validation score, uh, in for the set of parameters, optimization parameters for which we get a maximum validation score, we use that parameter to finally for final selection of the model, and we perform the test on the model with this particular values of optimization parameter. So this is the example. And this plot basically shows us the how the optimization parameters occurs for the maximum validation score. So this y-axis shows the number of occurrence, and the x-axis shows the different values for which we have trained the optimization, the for which we have trained our model with these optimization parameters. So the k nearest neighbor has in neighbor value, which can be changed from, which is changed from 1 to 16, and we can see that for the in neighbor value of 3, we have a higher value of the occurrence. Out of this 20 data set, we have a, you can see it is 9. So 9 times it, we find that the in neighbor value 3 gives the best result on the validation set. So we finally choose this value 3 as our optimization value for this model. So similarly, we find the best optimization parameter is 1000, which is a regression parameter C for logistic regression. Similarly, for random forest, the optimization parameter is called the N estimator. So this basically gives us the number of decision trees in that ensemble. So we have we found that 120 gives the best optimization value. And so SVM for the support vector machine, we have two optimization parameters, which is C and gamma. So that's why we have a, instead of histogram, we have a matrix presentation for that grid plot. So we can see that the maximum occurrence happens on gamma value of 0.001 and C of 100. And we have, out of these 20 trials, we have 7 times we have get these values, which provides the maximum validation score. So we stick to that value. So now this is the these are results for the different, these 4 models. So we have you can see this the 4 performance indicators: TSS, macro accuracy, SSW, and CSW are shown in this with different colors. So, and for KNN, we have the the values. I mean, all these 4 models has performed quite well, and the TSS values are very comparable. TSS and macro accuracy are comparable, but we can see that the SSW and CSW, the difference between SSW and CSW is higher for KNN and RFC, random forest classifier, whereas for logistic regression and SVM, we have get a very similar SSW and CSW scores. And indeed, it has a also has a higher values in PSS score itself. So from this, we can say that the logistic regression and SVM performs better because it has a higher TSS score, as well as it also has a similar SSW and CSW score, which is also higher. This similar SSW and CSW score basically indicates that the model works similarly and doesn't have any bias towards the flaring class or the non-flaring class. So this, which is a good thing. So this table, you can see these values are basically tabulated here. So we find a average TSS score of 0.967 with the logistic regression, which we found the highest in these 4 models. And following this, we have SVM classifier, which has a TSS score of 0.965, which is also, I mean, just very similar. So it can't actually distinguish between these 2 on this small difference. So both the SVM and the logistic regression basically performs very good and better than the other k nearest neighbor and the random forest classifier. Now we would like to know which feature is basically more important towards this classification. So to do this, we basically train the model with the features individually, so and check the TSS score for that. So in this left side plot, you can see the TSS score is shown in the x-axis, and the y-axis all the features are mentioned, and the total unsigned current helicity which comes as in the top. So it basically has the higher TSS score for individual training. So this is for and the ordering is like total current helicity, then we have a unsigned flux, then the unsigned current density, R value, total absolute twist, B square, total. So like this, and so we also generate this analysis and generate this plot for various other models also, like SVM and the k-nearest neighbor and RFC. So we find that there is some amount of change in this ordering. So to get a global estimation, because as we have already seen that all the four models are quite comparable in terms of their performance. So we should get a global generalized sense of feature ranking. We incorporate all these four models along with the F score and Y score. So now incorporating all these models into account, so we prepare a we summed up the points for this each models, and prepare a global ranking, which is shown in the right side, uh, plot. Okay, so in that we can see that the top five global features, which is unsigned current helicity and the current density, unsigned flux, R value, and the total absolute twist, which is the top five set of top five features, is also same with the what we get with the logistic regression. So now this is just to show you how uh, the events are distributed. The features for the event our data set are distributed for these top five parameters. So just to check for how it is meaningful, and the higher value we get, uh, is it actually manifested in the data itself by looking at the statistical analysis. So we can see that the positive value, I mean the flaring events are marked with the red dots, and the non-flarings events are marked with the blue dot circles. So we can see that there is actually a higher separation between the positive uh, class and the negative class, and the negative class is very clustered and narrowed, distributed narrowly uh, um, in at their mean value. So, and this is the case for almost all the five top features. And for R value, we had a for the negative class, which is shown here in the blue bar plot. So we can see somewhat two different cluster of points. So here and in this region. So these are basically showing some kind of bimodal distribution, because R value is calculated from the unsigned flux towards the on the polarity inversion line. Now, for the negative group or the non-flaring group, the active regions are often very small, and they doesn't show any clear uh, strong field, strong gradient polarity inversion line. So for them, the R value is very less or close to zero. So that's why we get a higher cluster on the close to the zero value for R value, and these are the some other non-flaring regions which has R value, but still the value is much smaller than the comparative to the flaring events. So now in this plot I have shown the how the model sensitivity is depends on the number of input features. To get this, so basically we uh, eliminating one by one, eliminating the features from one by one from our model, and uh, just par, just calculating the how its performance uh, each time. So so we have started with 14 features, as I already told in the previous slide. So with the initial training was done on the 14 features, then one by one we are eliminating one feature. So first, and as we eliminate the features, initially you can see there is no drop in the performance. So the left hand side plot is for the SVM, and the right hand side is for the logistic regression. By just looking at this plot, we can see that the performance are, I mean, the nature of these plots are very similar. So the the, the performance doesn't decay much in the initial stage, but when we eliminate more and more more and more features, after a certain point, the performance starts to decay. So this basically tells us that even the top rank feature is eliminated, the performance doesn't suffer much. That could happen because all the other features are cumulatively giving us the information or the proxy for the eliminated features. So, and this is same for all the models. So how much time I have?
You have 10 more minutes here.
Okay. So yeah. So one thing here is to notice that for the logistic regression, we have a when the performance starts to start falling. So after eliminating this ninth feature, so this falls is much sharper than the SVM. So from this we can say that maybe SVM is optimized better or performs better with the less number of features compared to the logistic regression, because it is less sensitive to the features elimination. Yeah. So now this is the correlation matrix for the all 14 features. So as we already seeing in this previous slide, so the model is not performance is not decaying much. So that can also happen because the underlying correlations of the data. So this actually is we find this in the this correlation matrix. So many of the input features are actually correlated among themselves with the high correlation. So which is a could be a cause for this getting this kind of model sensitivity behavior. So what if we optimize now all these previous plots and the model performance we are getting, that is for TSS value. We are optimize the model for getting higher TSS value, and we are basically judging on the base of the TSS score for this. Now, if we use SSW or CSW metric, then what will be the change in that? So I think it is a interesting work to do. So this is the uh, feature ranking plot, which I have shown earlier for the with the TSS. So when the model is optimized for TSS, now this one is for when the model is optimized for SSW. So, and if we now use shift to the CSW, then we can see this the ordering is slightly changed. I mean, there is some features which has increased their feature ranking when we switch from SSW to CSW, and some has gone down in the ranking. Just like the total unsigned current helicity, you can see if we switch to CSW, the current helicity is basically becoming more important in that case, and it goes to the top parameters. And similarly, like so other features also, some like R value, if you can see that. So R value is going down if we goes down if we use CSW as our optimizing variable. So now to quantify this, we basically calculate the change in switching to SSW from CSW, and the change in the performance indicator is basically shown in this plot. So this is basically the zero line is here, and so both in the both direction it is basically showing the magnitudes. So this is so for the top three parameters we can see. So if when we switch from switch to SSW from CSW, then this models has these three features has increased their uh, increase in their performance and goes up in the feature ranking. Similarly, for the bottom for five feature, which has goes down in the ranking when we switch to SSW from CSW. So that means if we use that means basically for SSW or the for the flaring, identifying the flaring regions correctly. So this R value, EPSZ, and the shear angle greater than 45 degree. So this basically has a higher impact on that. So they are basically better parameter for identifying the flaring regions compared to the non-flaring regions. Similarly, this uh, total V square and the total Lorentz force Fz and the total potential energy. These basically are better predictor for identifying non-flaring regions correctly. So now we have also tried to implement this model for real-time predictions. So as we can in this www.sesi.in/space weather, if we go to that site, we in real-time basis we can we basically um, generate flags for this for this all the visible active regions seen on the solar disk in near real time basis. So this is operational, and you can see this in this section basically you can see the total number of active regions visible for each day and the current flags for this regions. So and if we click at the active region number, so we can get the history of how the top five magnetic features have evolved over the past days, and how it is predicting how our model is predicting it as a flare positive, as a positive event or a negative event. So if we click on this circled region on the number, so we basically get this kind of plots. So as you can see, as in the bottom one, so all the five top ranked features are plotted over time, and you can see initially the features has a less lower values. So our model is not predicting it as a positive or flaring regions. So that's why. So we are getting no zero values for the fraction of ES flag. So fraction of ES flag basically tells us that during uh, so every 12 minutes the HMI magnetogram gives us new data. So for every 12 minutes we are basically sampling getting the data and taking the measurement and uh, identify if the region is a flaring region or the non-flaring region according to our model. So now these data are beamed in 6 hours window in the top panel, and in each 6 hour window, so we have a multiple number of such measurements, and out of that measurements, the number of time our model is predicting is as a flaring one by the total number of samples is taking in that 6 hour window is shown here in the as a fraction of ES flag. So as you can see, so it increases when the all the magnetic feature values are low. It is now detecting it as a flaring event. Now when the magnetic features are going to increase, that means maybe due to some emergence of the flux, or maybe the other reason due to change in the shape of the active regions. So these magnetic feature values increased, and we also start predicting the the regions as flare positive, and this increases. And for this, the later on, when the total features, magnetic feature values are already increased, then we are getting almost getting fraction of use flag as 1. So that means out of this 6 hour beans, so every time we are getting this region as a flare positive one. So like this. So these are maintained in this website on a personal basis. Yeah. So from this study, we basically compare in summary, we compare the 4 machine learning models, which are supervised machine learning models with input magnetic features given by the users. So these 4 models basically performs quite well for all this model, and we find that SVM and logistic regression, these 2 models outperforms the K-nearest-neighbor and the random forest classifier in terms of their higher true skill score, as well as the difference between their performance in pairing events and non-pairing events, as the SSW and CSW difference is smaller for logistic regression and SVM. So, and we have able to achieve a impressive true skill score of 0.967 with logistic regression, and we finally also uh, identified globally which magnetic field magnetic features are, I mean, giving good can be treated as good predictor for all these models. So these are turns out to be the total current helicity, current density, total unsigned flux, R value, and the absolute twist. So one thing is to note that all the extensive parameters are mainly is there in the top 5 input features, except for the R value. All other 4 are extensive parameters. Also, we have introduced the 2 new indicators, that is severe space weather and clear space weather, which has give new insights to assess the performance of models separately for the positive flaring dataset and the non-flaring dataset. So this study has been recently get accepted in Astrophysical Journal, um, and the archive link is here. So this is the first. Paper. It is still not publicly available. I mean, not published, but just accepted in like 10 days ago. Thank you. That's it from my side.
Okay, thank you so much, Shubhodip. That was a really nice talk. We have a question here from Devesh Bhattacharjee. He's asking why the error bars for the SSW is higher compared to the other matrices.
Sorry, can you repeat?
Yes, he's asking why the error bars for the SSW is compared to the other matrices. Uh, yeah, in that plot.
Okay, so this is I think this is from the statistical sense. I mean, so SSW is higher for SVM. Okay, so yeah, I think this is because the number of events are small in SSW. I mean, the pairing region. That that I think that could be the reasons for this getting higher variance in that.
Okay. Are there any more questions from the audience? If so, you can unmute your mic and ask the question. Okay, there are no show of hands, so I'm assuming there are no more questions. Okay, thank you so much, Subhadeep. And also Professor Martins, I think he has left. We can close this session for now, and we'll see you after lunch during the ML lecture series. Okay, bye, everybody. Thank you for joining in.
Yeah, thank you.